Okay, let's give it a go. Good afternoon. I guess you know me by now. I have a surprise for you. I have with me a bucket, used to be called red mud, Bauxite Residue, and I'm going to guide you through a process that we've been developing for the past 3 years. And the mission of the day is to communicate and show you how you can transform that into a binder. Now, I know we've been discussing about adding to cements 3% or something, but I want to go greedy. I want to use 90% of that, okay? And I want you to see every step of the process, so eventually you understand yourselves and you make your own judgment, okay? Come with me. Now, we're going to visit container number 1, and I have the first surprise for you. Where's number 1? That was number 3. Is that number 1?
Hello, Yannis?
That's Michiel. Michiel is doing his PhD with us. Michiel, I have a surprise for you. I have this bucket of this liquid thing. Can you do something with it?
Of course, it looks very nice. We can do many things with it. Do you want something specific? Maybe a building material?
I wouldn't mind for a binder or cement alternative.
Okay.
Sustainable if possible.
Yes, we will make it sustainable, and I will show you. You can join me. So, what we do first is put this material inside the mixer, and we can put additives inside, make it even more liquid, less liquid, and then we can run through the container. So I will show you how we mix the red mud, how we add the additives, and how it is pumped through. So now we have seen actually where we bring in the red mud, we mix with the additives, and then it will go to a bigger tank. And that I will show you in this beautiful container. So the red mud comes in from outside, it goes into this tank. It's a double layer tank, so actually what you can do is heat up the temperature, so it can be very nice, for example, for alkalization, dealkalization. What you then do is actually you make everything very nice, and then it goes to this filter press. So the solution is pressed out, and the solution can be recovered, for example, to make inorganic polymers. Then the dry material falls out in a screw mixer. It is actually a bit broken up, and then it can get transported and pelletized into a very nice product. And I will show you now how the mixer actually works. Okay, it makes maybe a bit of noise, but you get a very nice product out of it. It's actually a pallet. We can make every shape you want. Now we can make sausages.
And what am I going to do with that, Michiel?
Would you maybe like a bucket of sausages?
I would love to, but what am I going to do with that?
Maybe you should check out the container with the oven.
Well, now let me get this straight. What have you done with sodium?
We want sodium inside, so we left it in.
Why do you like sodium?
It makes the material even more reactive. For inorganic polymers, sodium is perfect.
So you mean like a flux?
Yes, it's a very nice flux.
Would you add anything else besides bauxite residue?
We can add fluxes up to 20%, but we try to keep the flux amount as low as possible.
And let me get this now straight. This flux that you add, are these some kind of expensive exotic material?
No, it's what you can find everywhere. It can be limestone, can be silica, but the purity actually doesn't matter. So you can go for low-grade materials. And that's actually what makes this process
Has
nice.
that been proven, published or something? Is that science or is it some kind
It's all published online by Leuven, and more beautiful things will follow online.
And one paper tomorrow by Michiel.
That will still maybe be next week.
Okay, now let's see what I can do with that. Come with me. Put the mask on, and I'm going to try vitrify that, and I have an idea of someone that perhaps can help me. Come. Now, at the end of the corridor, you will see Tobias. Toby, hi. I have this bucket from Michiel. He says it's an amazing product, and he says perhaps I should be vitrifying that. Any idea?
The best idea is that we go to our second container where you can actually transform this material into something different. So what you can see here is our heat treatment unit operation. And what you actually can see here is the furnace itself, which is an induction furnace. And we have a generator in the back, which generates the heat basically for this furnace. And what we want to do here is we want to transform this material at high temperature, for instance, 11 to 1300 degrees, into something which we can use then to make a binder material out of it. So what we do is we put this material in the furnace inside, which we can maybe have a look at. And as mentioned, we go to temperatures around 1200 degrees where we partially melt or sinter this material. And the next step is to quench this material very fast. So basically, we want to transform the melt that we form in the furnace into something glassy that is reactive as a binder material. When we quench that material, what we basically get out of the furnace looks a bit like this. So we have a slag material, which you can see also has changed the color. That depends on the certain additives that we mix with the bauxite residue in the previous containers. So basically, Yannis, I can give you now the next material, which is a slag.
Wow, wait. It looks nice, but let me understand a bit more. That for me is granular, and I want that into a binder. I want cement. I need it more fine.
Yes, exactly, Yannis. The next step, what you need to do is you need to make this finer, this material, because you can see that now it's relatively coarse still. So we get it relatively coarse out of the furnace, really like these granules, what you can see. But the idea is now to go to another container where we make it fine, that it looks like a cement.
But let's say now, if I'm a cement guy, you are also using a high temperature process. What makes you think that your process is more sustainable than a classical cement making?
So the idea what we have here is we go to a much lower temperature than conventional cement production, because cement production is at 1450 degrees in a rotary kiln, while we think we can go much lower in temperature with using this furnace, what you have just seen. So the minimum what we can go is 11 or even 1000 degrees, depending on the additives that we have, and depending on the cooling of this material. So if you have a very fast quenching in water, we can make a material that actually acts like a cement, works like a cement. But as you mentioned before, we need to get it in a finer size.
But are you adding any limestone inside? Do I have calcium carbonate as additive?
So as Michiel probably already mentioned before, we have certain additives which we can put together with the red mud inside, which can be theoretically limestone as well, but much, much lower compared to conventional cement production, because there we use around 80% of calcium carbonate as a raw material. While in this case here, we have actually more than 80% of red mud as a raw material. So the main additive we have can be silica or calcium carbonate, but that will be only 10%.
Tobias, doesn't that look like a bit like copper slag?
Actually, it is relatively similar than copper slag. So we try to actually make a kind of copper slag out of the red mud. As you mentioned correctly, we have a similar chemistry in the bauxite residue and in these copper slags. So we basically try to mimic this copper slag in chemistry and also in mineralogy. And what we get is something like this.
Wait. Now, let me understand that right. We have this calcium aluminum silicate system. That's the classical cement, right? And now what we are doing, we're making these iron silicates, maybe with a bit of calcium. So we are creating this parallel universe. Is this the whole story?
Actually, you're right. We are creating a completely different binder system, which is based on these iron silicate slags. In this case, also because we have in the bauxite residue still aluminium as well, and also calcium, an iron calcium aluminum silicate glass, which is basically a novel binder system.
Okay, I want to find out more. Can I have that?
Of course.
Thank you, Toby. Thank you. All right, let's explore more stuff. Now it looks like that, but I want this to become a binder. So it means very, very fine. So I need high specific surface. You need this thing to react. So let's see what the options are. I have another possibility for one more container to look at, and I think it's over there. Let's see. We need now milling. All right. One more door to knock. Hello, Timis. Welcome. I have this present for you. Can you just make it fine?
This is a very nice lab. You get Kentucky?
Yes, I did.
Great quality.
Thank you.
So we will get this coarse. We will get this coarse slag, and we will mill it into a fine powder that will produce us a high quality binder. This is the milling and storage unit of the facilities. Please take a look. This is our redesigned ball mill attritor. We use steel balls and slag that we add into it pneumatically to grind the slag into a fine powder. Then the fine powder is also connected pneumatically and automatically during the whole process, and we can change a variety of parameters in order to get a final product that has the properties that we want. The final product is collected pneumatically, as I said, into one of the 6 solid tank silos that we have in the back. Those silos at the bottom are equipped with a screw that promotes the material into a collector, using also a small vibration machine to facilitate the movement. And then the materials we need in the correct amounts that we have selected in the operation unit that I will show you in a while are sent pneumatically to the mixing container. Then, after milling and collecting, we can also fill the rest of the silos with other materials that we need for our mix designs. Other aggregates, such as unmilled slag that can be used that way, or sand, or other binders that we can use together with our milled slag to produce a high quality binder. And the operation of the whole unit, this container and the mixing container, is done from this touch screen, where we can select the quantities of the material we need to forward, and then the operator of the next container only has to press start in order to start mixing. Now I will demonstrate you how easy it is to select the silo and start the attritor. And out of the attritor, we have the finely milled slag, this fine powder that will be our main binder. Now I can give this to Yannis, so he can this time only manually proceed to the next container.
Well, before I take that, I see you have 6 different tanks. Can I have blended cements?
Of course, in the 6 tanks, we can fill them with any material we need. And we can fill them with different binders and aggregates, and then select the quantity we need from each, and automatically they are moved into the next container. If we don't add liquids, then we can just blend the cements or the aggregates with them and take out a ready mixed mortar. Ready to mix.
So you're saying I can get different cement, I can get different mortars. Can I get some refractory binders from here?
Of course. There's no limitation in the type of materials you will use.
Nice. So it's like pretty much like making the same 1, same 2, same 3. But I understand you don't call this ordinary Portland cement.
No, this is extraordinary. And it's extraordinary levels.
Our marketing. Let's go to the next stage. Thanks. Have success. Okay, well, I have a powder now. And let's see if I can do something out of that. I guess we can put in a bag. I mean, a cement, buy that in bags. But I can also make perhaps final building materials. Because you can't really call it cement, you call it a binder, since the standards do not allow that. And the standards are basically, drafted by the same people. Kind of interesting exercise, actually. So if I make final building materials, final blocks or tiles, perhaps my market penetration is easier. And I see a guy I know. Tobias? Hi. What can you do with that?
Hi, Yannis again. You're back. Nice
Surprise,
to see you again.
surprise.
So what if I just show you our next container, which is the mixing and casting container?
I've been very much interested to see that one. How do we start?
So I think Eftim has already explained you a bit what we actually do in the previous container. So we want to transfer certain materials to this container here where we do the mixing and the casting of actually binder materials. So the first thing what we have is our slag powder material, so our binder. And we want to, of course, mix that with an alkaline solution or another liquid, for instance, to make blended cements. And this is fed in this container here, what you see in this mixing vessel here. And it is already weighed there. So basically the recipe what we put in the previous container is weighed in here so that we have the correct proportions for our binder materials which we want to make. The next step is then we want to, of course, mix this homogeneously. So we want to mix the solids and the liquids together. And for that we have a very nice tool which is a so-called high shear mixer, which you can see here next to you. Basically what we then do after that mixing, so we have a homogeneous paste consisting of a solid and a liquid, we can discharge it by just using here one of these joysticks here, which leads to an opening of the high shear mixer, so we basically can discharge the material from there. So that's how it then afterwards kind of looks like. We have a mix of a solid and a liquid, which is basically our paste, which we want to cast in certain molds. What is then very helpful for us in this container is that we have a kind of conveyor belt where we can transport this material to a next tool where we do a so-called vibration. And the idea of that vibration is to take the air out of the material and to get it really filling the whole mold. Then basically, the only thing what we need to do is still we need to cure our samples. And there we have different possibilities how we can do that. So one possibility is just to cure it at ambient conditions. So at a room temperature, for instance, in a curing chamber. Or we can also autoclave our samples. So what we can do is we can subject it to hydrothermal conditions because then we might have a better reaction of certain phases. And what we get in the end are basically our building products, which you can see now with Yannis.
Well, I'm quite convinced actually. But now I changed the role. I'm Yannis, a very tight lab coat. Yannis, bare body, and there perhaps a colleague. So come with me. You will see now the last step. So to recap, that's what it comes from the alumina business. It's a slurry, right? You see it here. what we do afterwards, we add 20% maximum of additive,
Yanni, we can't hear you.
There is poor sound.
All right, if I speak closer to the microphone?
Yes, better. It
All
was
right.
probably covered.
Okay, all right. So you've seen the second step of the process. That was the container number 1 still. Then we do the vitrification. We get that thing that looks like a slag. So in fact, this is a call for an alliance of all the non-ferrous metallurgical industries. And then we do the milling and we get that thing, which is a powder. Now, if you combine things, because I still have some alkalis in the first bucket with the slag, I can make different final products. I can even use fresh BR without being thermally treated. And you can see, for example, facade tiles that are now presented in this capture, or you can see black tiles, again, for facade applications. And sky is the limit. These are porous materials here. You can use red mud again as a pigment. You can have fibers of all kinds of fibers, metallic fibers, polymeric fibers. You can do 3D printing. Check out the YouTube video. We did that. You can do terrazzo and more stuff. Beautiful enough, if you heat this thing up, it becomes ceramic. So you don't lose any of the performance. On the contrary, you win much in strength. And fun enough, all of this is positioned on a table that is made out of copper slag or vitrified bauxite residue. Now, I think we've done it pretty much all. I mean, we are the scientists. We've done the upscaling, and we've been also today the actors. And, you know, that's the crew and that's the film that you've seen in your eyes the past, I guess, 10 minutes. And I think that should be about the end. Now we can go back into the science and perhaps answer your questions.
My work is inspired by African patterns, circular economy, ecology, and recycling. I made my artworks from the pigments who were given to me by the KU Leuven. I'm very grateful for that. Let me briefly introduce me. I've been drawing since a young age, and later I joined the Academy of Fine Arts in Brussels at the age of 15. On January 2019, I decided to do a challenge for 1 year, 1 drawing per day on the theme of Africa. Why Africa? Because Africa is the nest of humanity. It's fascinating. Africa is rich, both culturally and ethnically. The charm of its imagery provides endless possibilities for creations. On February 2020, I began a new challenge, making creation on the theme of African graphic patterns as well as circular economy, from recycled support such as all and already used canvases, second-hand furniture, old page from encyclopedia, and by using the KU Leuven recycled pigments. Pop Africa is born, my new art series. Each work hides a sentence or a slew of words on the theme of recycling and ecology. In the Himba painting, my main point is that the viewers will identify themselves to this woman from a famous tribe in Namibia called the Himba. As you can see, it's a young African woman who has a confident and serene posture, but above all, it expresses the fragility of this ephemeral world where nature is in danger and where ancestral tribes risk extinction, as they are becoming fewer and fewer. The Himba's beliefs testify a poetic vision of life. For them, already before birth, all humans have their own song and their own voice. The mother, before conceiving her child, asks the universe to hear this song, so that she can follow him all their life. The Himba painting has been donated to the KU Leuven as an acknowledgement for its participation in my project.